Mm-hmm. All right, so welcome to the 13th day of the Bronco Show. Okay, so what we're going to be working, first of all, let's just do one to just keep our brains a little bit active. You guys have that list of really important derivatives? Yeah, that's a problem. Do this one for me. Do that just to get yourselves in the groove. So remember, the natural log has the derivative of 1 over x. But now it's going to be not 1 over x. It's going to be 1 over. So I'm going to the wrapper on the outside is the natural log, right? So if I have a natural log of dog, all right, and I take the derivative of that, I get 1 over. I don't care what's in the natural log. And now you would have to find the derivative of dog. Okay. So I would have dog prime over dog, whatever the heck that is. And what do you wind up getting? One over sine x times the cosine of x, which is cotangent of x. Whatever dog is, I don't care what it is. Because you deal with the wrapper first on the outside, and then, so you take the derivative of natural log, which is 1 over whatever's inside, and then once you've opened that box, you take the derivative of what's inside. You have to take the derivative of the outer layer, then you take the derivative of the inner layer. Because remember what the product rule says. That's what you're doing. You're making a substitution, right? So this becomes the natural log of u. Yeah, you can do it multiple times. You can wind up getting multiple derivative parts here. This can go down the road. So this becomes ln of u, right? And then so I've made my substitution, and now when I take this derivative, the derivative of y with respect to u is 1 over u, right? That's him, 1 over u, of whatever the heck u is. So you wind up getting dog prime over dog. Or in this case, sine prime over sine. And sine prime, which no one ever says, the derivative of sine is cosine. So you get cosine over sine, which is cotangent. Without doing the work in your mind, try this. Oh, it applies to everything. It's calculus. It's all, Well, that's just because trig is fun. What is it? Negative tangent, right. Because the derivative becomes over cosine times negative sine. Negative tangent. Okay? The derivative of sine is cosine. The derivative of cosine is negative sine. From first principles. Here. Right? That's first principles. This is cosine is cosine, cosine, sine, sine, right? Yes. No, cosine, cosine minus sine, sine. Cosine of x, cosine of h minus, remember them, is from the half and double angle formulas. Because that's how you get the half and double angle. Because, so cosine of 2x is uh, cosine x minus sine x. And if this was, for example, this is how I remember it. Cosine of 2x is the same as this. And then this would become cosine x minus sine x, sine x, which is cosine squared x minus sine squared x, which is what this guy is equal to. Right. Anyway, moving on. That's really bad. Wrong code. Don't ever do that again. Bump, bump. Right? And now I'm going to group like terms and factor out what I net. And we wind up with right? So I split. I did a lot in that step. I grouped the first and third terms, factored out a cosine x, which left me with cosine of h minus 1 all over h. And I also split my fraction because now I've got to get my sine x, which is sine h over h. Now sine h over h is 1. This becomes 1. And when I take this limit, that goes to 0, which leaves me with negative sine x. Okay? Do you remember when we first started playing with this, I showed you two graphs? One that looked this was sine x over x. And took the limit as h or as x approached 0, it was 1. And here, 1 all over x. Okay? Cozy, comfy, warm, fuzzy. Everyone happy? Fan flippin-tastic. So, all right, actually, I'm going to undo that because I'm going to keep that. All right, so now we get to play with one of the most powerful tools in differential calculus, the product rule. They all deal with exponents somewhere around the way. Wait until I think it is. Wait until the 16th day of school, which I don't think you have my class for, because that's when we talk about tetration, which is exponentiation on steroids. It is powerful. Bad joke. All right, so let's just that are multiplied together, and they're both functions of x. For example, what if I had this? How would I play with that, besides first principles? You see, in this case, we have two functions, x and sine of x. Or maybe something like that, you know? Where this guy is f of x, and this guy is g of x, okay? And we want to have a way to play with this. Now, I'm not going to go through the long drawn-out derivation of it, but if anybody is thinking about doing like the Newton-Leibniz difference between the two calculus, the two approaches to calculus, Newton's approach to this with infinitesimals is pretty neat, for those of you that are interested. This is equal to Leibniz. We use this is Leibniz notation. No. That's modern. That's modern mathematicians being lazy. So when we do this, we wind up getting, and I'm going to mix notation here, which is really bad form. So sometimes you see it as, even in shorter notation, where u and v are functions. So they both get a derivative, and they both are left alone. Okay? Everybody gets a turn. You can think about it that way. Everybody gets a turn getting a derivative. All right? So this is actually really straightforward. Okay? If you have two things, take a derivative of one, leave the other alone. Leave the first one alone and take a derivative of the second. So let's take my okay? Try it and just see if your intuition is correct. Some of these kids have been moved off of the roster, but that might be misplaced in the wrong class. So see if I know he's still in my class. Check in fourth block.
I saw the name.
He's still a student of mine.
Okay. That one?
No.
Yeah, I have it.
What block are you doing?
Um,
You're on 4?
yeah. What is... So she has two perpendicular bisectors, and they're both half. I don't know what to do with it.
Just give her the half. Half. What did you wind up getting, guys?
2x times.
Okay. And if you needed to, you might need, you could factor out an x or something like that. Okay. What do we do this for? Okay. Let's try.
Can you give us a real world example of this?
That's probably going to be a word.
Yes, it is. Try this one. So this guy not only uses the product rule, but he uses the chain rule. Always attack it from the outside in. If you were to walk down the sidewalk and see that equation sitting on a bench, that's probably a good thing. So I really, too bad. It's too bad you didn't say that loud enough to be picked up on the microphone, and I'm really glad you didn't. All right, but if you walked up to this, what is this thing? What is its outermost wrapper? No. Is it a sum? Is it a multiple? Is it a sum? Is it a product? Is it a power? What is it?
Power. It's a multiple.
It's a product. It's a product of two things.
Cheers.
And one of those things is a power.
Cheers.
Right?
So we have to keep the product rule.
You do the product rule because that's the outermost wrapper. So if you want, you could do this. For example, let's call this U, let's call that V. All right? So it's going to be U prime V plus U V prime. And now, when you find U prime, you're going to have to play with the chain rule. Right? Because that's what you're doing. You're going from the outside in. Time. Right? Because this is the 3 that was my exponent. Right? And then this 3 came from the derivative of the inside of him. Right? Yes? Okay, good. And now I have V, which is sine x. And now it's U times sine. Derivative of sine is cosine. Does that fly? So that's how you play it. You like if you think about it from a programmatic standpoint. Who here does any kind of programming of any kind, even if it's on your calculator? Okay, a handful of guys have done some programming. All right. If you are looking at you go to a piece of code and you look at it, the first thing you might see is a loop. And within the loop, you then see, the definition of a script, or the definition of, well, actually, you would put classes and script up front if you were doing Java and whatnot. But like, you're to go into the loop. And then once you're in the loop, then you can deal with what's inside. So you have to think about the outermost thing that you're dealing with. The outermost thing on that Y is a product. It is a product of two beasts. Ooh.
Wait, can you show us how to solve that?
We just did. Well, no, you would simplify it. And that's about as, you don't want to expand that. That binomial to the third power and binomial to the second power. And the reason why you don't want to expand that is because once you've expanded it, you can't expand it with the, because one by sine, the other one's multiplied by a cosine. So you're going to wind up getting here, you're going to wind up getting three terms. One of them is x squared, one of them is x, and one of them is a constant. But all three of them are going to be multiplied by sine. And then this guy is going to give you four terms, an x cubed, an x squared, an x, and a constant. And then all four of them are going to get multiplied by cosine. So you're going to wind up with 7 terms, 3 here and 4 here. I see your hand. 3 here and 4 there, right? Because when you take a cube, you get x to the third, x squared, x, and constant, right? And all 4 of these get cosine tacked onto them, which means you can't combine them with any of these guys, any of these 3, because all 3 of these guys have sine attached to them. You see what I mean? If you're going to wind up just getting a big mess of 7 constants, sorry, 7 functions. Ew. This is a lot nicer. And no, I am not dividing by 3. Hand. This 3, this second 3, this second 3 came when I took the derivative of the inside of him. Okay, my first, okay, I did u and v. So this first piece, u prime, okay, is the derivative of that fellow, right? So the outermost wrapper is a cube, right? So I take the derivative of that, and I wind up with 3 to the 3x plus 4 squared. The coefficient, exponent becomes a coefficient, you reduce the exponent by 1. Now, that's my outer layer. Now that I've pulled the wrapper off of the box, I can go inside and take the derivative of what's in the box. And what's in the box is 3x plus 4. The derivative of him is just 3. Does that make sense?
Yeah.
Yes? Or are we lying to our
Oh,
teacher?
yeah, it makes sense. I don't see how it connects to the derivative of u times v.
Because I haven't even gotten here yet. When I do this, all I'm doing is that. And then I put the v in the other stuff. How about this? Why don't we hit the boards on this one?
Let's hit 'em.
I'm going to pause the Ronco show for these exercises. And that is the Quotient Rule, and this episode of the Ronco show has been brought to you by the product and Quotient Rules. And the number 3.